Welcome again in my video tutorial, and you can subscribe my channel if you like. In this video tutorial, we will learn about the design of simply supported one-way slab. And in this video tutorial, I will explain about the design steps so quickly. The design steps are not more and not so difficult. Only the design steps arranged here in the required order. Now, starting the design steps. Firstly, I request all of you guys, if you are watching this design, you have to download IS 456 2000, from which we use the values, codal values codes IS 456 2000 RCC code. Now, step number one, or the given span, clear span of slab, find the Ly by Lx value. That is longer span Ly divided by shorter span Lx value. If the value is greater or equal to 2, then this is one-way slab. If the value is less than 2, it is two-way slab. We only explaining here about the one-way slab, but it will be applicable for both one-way and two-way slab. For the one-way slab, if Ly by Lx is greater or equal to 2, it is one-way slab. Then we calculate the effective depth from the deflection criteria. Number 2, total depth equals to Lx by 25. Calculate Lx by 25. Lx is shorter span divided by 25. And effective depth D equals to full depth minus effective cover, means clear cover, minus diameter of bar divided by 2. And then we calculate the effective span. Effective span is the minimum of clear span plus effective depth, or center to center length. Here we calculate the effective length L effective equal to Lx plus effective depth D. And in codes, the clear cover for different condition is explained. Now I am going to show the clear cover data in IS 456 2000. This is our code IS 456 2000. After downloading this, press Ctrl F and search the nominal cover, nominal COVER cover. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17. Here is table number 16, clause number 26.4.2. Here the nominal cover for exposure mild, moderate, severe and very severe is given. We mainly generally use for mild or moderate exposure, so nominal cover we use 20 to 30. We use 20 or 30 or 25, in between 20 30 normally in moderate condition and mild condition. According to code, for mild exposure, the nominal or clear cover should not be less than 20 mm, and for moderate exposure should not be less than 30 mm. Okay, now I will return to the our slide, and in this, after the effective depth calculation and effective span calculation, we will calculate the factor load of the slab. The total factor load is the sum of dead load plus slab load plus floor finish load into 1.5. Here 1.5 is the factor of safety, where dead load equals to concrete unit load. For reinforced concrete, 25 kilonewton per meter cube, and for unreinforced concrete, plain concrete, the dead load is 24 kilonewton per meter cube unit load for concrete. Concrete weight. Reinforced concrete. I am searching reinforced concrete. Reinforced concrete. Reinforced concrete. Reinforced concrete. Reinforced concrete. Here is explained. Dead loads. The crushed natural stone aggregate may be taken as 24 kN per meter cube and 25 kN per meter cube. Here, unless more accurate calculations are warranted, the unit weight of plain concrete and reinforced concrete are correspondingly plain concrete 24 kN per meter cube and reinforced concrete 25 kN per meter cube. Now, I have explained about the dead load. 25 dead load kilonewton per meter cube into B into D kilonewton per meter. We calculated the load in kilonewton per meter. That is, dead load equals to 25 into B into D. D capital D. B we assume the unit width, that is 1000 mm. That is 25 into 1000 into 1000 means 1 meter. 25 into 1 into D in meter. Dead load plus live load equals to live load will be given kilonewton per meter square in kilonewton per meter square, and we multiply this by the value of B. B is unit, that is 1 meter width. We assume the 1 meter width of the slab. So live load equals to given load per meter square into B means 1, and floor finish also same, and multiply this value by 1.5. We calculate the factor load in step 3. Then step 4, factor moment equals to the UDL, that is load calculated in kilonewton per meter is small w WL square divided by 2. No, WL square by 8, where L is equal to L effective, not LX. WL square by 8. And in step number 5, find the D required and check or compare with the calculated effective depth. The calculated effective depth used should be greater than the D required, that is effective depth required. We can use MU equals to 0.36 XU max by D into 1 minus 0.42 XU max by D FCK BD square, or from the code for FE415 MU equals to 0.138 FCK BD square. MU is calculated in step 4. 0.138 FCK is M20 for concrete of M20 concrete, for M20 concrete FCK 20 BD square. B is 1 and D is 1, means here we use in mm 1000, and D square we calculate the D value and compare with the D. If the our calculated effective depth is greater, then it is okay. And I will show about the XU max by D and MU value in RCC code. Now, in RCC code, XU max by D. Search XU max by D. XU, okay, XU max by D value for different grade of steel. Here for steel of Fe250, XU max by D is 0.53, and for Fe415, XU max by D is 0.48, and for Fe500, that is TMT steel, Fe250 is mild steel, Fe415 Tor steel, and Fe500 TMT steel. HYSD steel means Fe415 and Fe500. For Fe500, XU max by D value is 0.46. Similarly, for the maximum limiting moment for Fe250, mu max equals to 0.13, no, 0.148 FCK BD square, and for Fe415 FCK BD square into 0.138, and for Fe500 FCK into 0.133, that is 0.148 FCK BD square, 0.138 FCK BD square, and 0.133 FCK BD square respectively for Fe250, Fe415, and Fe500. Here table number not given. In 38.1 S456, the value of XU max by D for Fe250 is 0.53, for Fe415 0.48, and Fe500 0.46. And I also show about the moment. Control F search, Control plus F, MU moment, MU max, MU max. One is show about the MU. So searching MU max value, MU max value. Okay, MU max value is in table this RCC code. MU max value, maximum moment resisting capacity of concrete structures, maximum moment MU max. mu max, mu max, mu max. Small time will taken for these shear test footings. Okay, mu max, maximum moment, maximum moment. Okay, here is moment of resistance for rectangular and T sections. In clause no in Annex G clause 38.1 the moments formulas are given. Here mu max, mu limiting equals to 0.36 x max by d 1 minus 0.42 x max by d fck bd square. For Fe4 and 5 we put x max by d equals to 0.48, here also 0.48, and this calculation we get the 0.138 fck bd square. Similarly for other 0.133 fck bd square for Fe500 and Fe250 0.148, no 0. Yes, 0.148 FCKBD square, 0.148 FCKBD square, 0.138 and 0.133. XU max value 0.53, 0.48 and 0.46 for FE250, FE415 and FE500 respectively. Okay, I have shown you on this course. Then again, after calculating the D required value from this equation by using the MU value calculated in step number 4, we compare this effective depth with our assumed depth or our calculated depth. Our calculated depth should be greater than this obtained value, and it will always probably always be the good, or our d value will be greater than the calculated d value normally in general. Okay, after this, in step number 6, find the AST area of reinforcement for main bar using the diameter 10 dia bar, and from mu equals to 0.87 FIAST into D 1 minus FIST FCKBD. This is also shown in code here. 0.87 FIST D 1 minus ST FI by BD FCK mu. We calculated the AST value, that is area of reinforcement, and we calculate the spacing in step number 7, that is spacing equals to width B, that is 1000 into area of one bar, that is pi d square by 4, diameter 10 pi d square by 4 divided by AST calculated in step number 6. And after calculating the spacing, we compare this spacing with 300 and 3D. If we if the value is less than 300 or 3D, we use the value of spacing calculated, and according to the code, the maximum spacing should not be greater than 300 or 3 times, or 3 times diameter. Sorry, the spacing maximum spacing should not be more than 300 or 3 times d, where d is effective depth or calculated spacing. Whichever minimum, we use the value for the spacing of the main bar. And for the spacing, we use the minimum value of 300 or 3 times the effective depth 3D, or this calculated spacing value for the spacing of the main and distribution bar. After calculating spacing for main bar, we use 6 distribution bar and calculate the spacing. For the spacing, the area of reinforcement AST for distribution bar is given in the code as 456. This should be 0.12% of the cross section, that is AST for distribution bar equal to 0.12 divided by 100 into B, that is 1000 into D is total depth according to the code for Fe415. But for Fe250, the AST for distribution bar equals to 0.15% of the cross section area, and the bars are bented at the joint at support, so top and bottom bars are shown in the cross section of the slab. So after designing this all, we should check the slab is safe in shear or not, and we also should check the deflection and development length criteria from the IS 456 2000 code. In this lecture, in this video tutorial, I only explain about the this design steps of simply supported one-way slab, and we will do the numerical example in our next video tutorial. And for the video tutorial, you can find this video tutorial of the numerical example for the design of one-way slab in my channel. Thank you.